Good. Well, welcome to this an interesting aspect to this 2 days of the workshop. And this is a format that I think actually Steve sort of helped pioneer in terms of interacting with scientists at SFU and trying to change the dialogue so it was more focused on some accessible and insights into what it is that drives scientists, what their favorite colors are, things of that sort. Steve's in BPK with myself. He's been there for a while. And Victor, some of you who've been on the call for the last 2 days know who he is, but he's a director for the Institute for Neuroscience in Marseille. He's also a theoretical physicist and has been working on dynamical systems in the brain for some time, and he's a close collaborator of my own. And what we're going to do again is have just a chat between Steve and Victor for say about 25 minutes to 30 minutes, and then just open it up for just a free-form discussion. This is really meant to sort of have a dialogue. So there's no real intention or any sort of mandate other than just to have a good chat and see what's going on. So with that, I'll turn it over for Steve and let the party begin.
All right, thank you, Randy, and thank you, Victor, for the opportunity and for visiting us. And I'm really looking forward to chatting for the next half an hour, and then again we'll open it up for questions. I wanted to start by asking you about the value and in particular, like the specific outputs from the simulation model, the virtual brain that you've worked on, and how they're important both from a basic science perspective and a clinical perspective. So the virtual brain model is something that you've worked on with Randy and others for over 20 years, and it's a free open source software package for exploring network mechanisms of brain function in health and disease. And we enjoyed lunch on Tuesday, and I asked you, and we chatted about this sort of question, and you mentioned that a primary role of the software is what you call data augmentation. So you input patient or participant specific data from dynamic neuroimaging, and the model provides specific outputs. So let's consider the context of the work that you've done in epilepsy, where you've developed these patient-specific models, which are now being used in a large clinical trial. So to return to my original question, what are the specific outputs from the virtual brain model that are of greatest interest, maybe starting, let's say, with clinicians, and then talk about those outputs that are of greatest value to researchers?
So thank you for the question, first of all. Yeah. By outputs, you probably mean what is a particular use for clinicians and researchers. Yeah? The virtual brain platform allows us to perform simulations of brain activity. One particularity of the virtual brain is that it's not just simulating source activity, but it's mapping also the sources, so the areas of the brain where the activity occurs, onto sensor signals, fMRI, EEG, and EEG. This is actually what we measure in the real world. No one in the world can measure source activity. We can get very close. At the end of the day, you always have sensor signals. This gets us extremely close to the patient and to the patient applications, number one. Number two, talking about medicine. At the end of the day, as a treating clinician, you're always in an N=1 situation, looking at one patient, his or her specific situation. So you want to actually tailor your decision-making process to this particular patient. by merging the patient's own data into the virtual brain model, you can actually tailor this process and make prediction for this particular patient, also in terms of brain imaging signals that you then can compare against the real world data that you have. Yeah? So it's a tailoring, the personalization, and because it's a simulation platform, you can actually ask questions that cannot be answered in real world situations. You mentioned epilepsy, for instance. In epilepsy, drug-resistant epilepsy, we have as a therapeutic approach, you take a surgical approach and you want to resect the epileptogenic zone. What are the best ways to resect the epileptogenic zone? What if there are multiple hypotheses? What are the consequences there? This you cannot test in the patient, but this you can test in the patient's own virtual brain and perform systematic studies, optimize the procedure, and then advise a clinician. Yeah? This is for epilepsy, but I think it's very obvious that you can translate this also to other pathologies.
Okay, I'm starting to get a better idea of the kind of virtual experiments you can run in the case of epilepsy, and maybe we can, if we have time, we can return to that. I wanted to ask you why study brain dynamics in the so-called resting state. And in the context here is that I know that that is one of the major focuses of your work, to study, to measure and model neural dynamics in the resting state. And that allows for models to be built from standard neuroimaging data where people are resting quietly during the scan. So I can see that that's a huge advantage, that all of a sudden, your models are applicable to so much data and vice versa. But what essential information is provided by studying brain dynamics in the resting state? And I might imagine, like, is there also value in studying, for example, motor imagery?
Yes, it is, of course. But first of all, the resting state, when you look at the brain imaging data, the resting state is not just a simple idle state where not much is happening and the brain is just in an idle expecting state. No, on the contrary. What is actually happening at rest is that there is an exploration of a large repertoire of different networks. Yeah? And so there is a large dynamics, complex dynamics that is ongoing in the brain during this resting state. And many of these network activations that we observe are activations that we know from task paradigms. You mentioned the motor paradigm from attention studies, working memory, from visual stimulation studies. So there are network activations that are being systematically visited and expressed in very characteristic fashions. So there is hence a functional representation, even though that the function itself is not executed. Also in imagery, you can, for instance, ask a person to imagine a particular task, and very classic, very specific networks are being activated. Then, having said this, the resting state itself is also a criticism that comes up very often is that the resting state is a very badly controlled state. I invert this and make this an advantage. There is a wandering, mind wandering, again, a visitation of different networks and task relevant scenarios. This is actually exciting. This richness is meaningful. It is meaningful in the sense that it tells us something about what is happening in the brain, about capacities. Already the fact that resting state is so complex. So it's indicative of some of the properties of the cognitive architecture that is behind that. Second, it changes across diseases. It changes across the age, for instance. So we can actually use this resting state and extract biomarkers that allow us to describe it in more details and start quantifying, maybe stratifying individual groups. Biomarking is one of the big challenges that we have in neuroscience, especially if we want to go into clinics and translate our knowledge into diseases.
Okay. My next question has to do with validation and how you validate your models. And I realize like that's a big question. I mean, there's so many different types of validation, internal, external, construct validity, etc. But usually when we, think about a mathematical model, we try and, undertake efforts to validate that model. And I understand your model is constructed a lot based on dynamic neuroimaging, like it is, it's, as you say, like augmenting the data. But are there efforts that you undertake, and maybe you can describe those, to validate the model? I know a lot of your work is on human brain function, but at the same time, you've also developed animal models, and I'm wondering if there's a role of animal models in, the refinement and validation of the models. Mm-hmm. But you just talk about the general area of validation.
Yeah. So animal models are being used. In the virtual brain, we introduce subjects' own data. But sometimes the quality of the data is questioned. For instance, we use DTI, diffusion tensor-weighted imaging, to reconstruct the connectivity. We're not really, it's a representation of the connectivity. It's not really the connections. How good is that? Yeah? These are aspects we can test only in animal data, where we can actually have access to the real existing fibers connecting individual brain areas. So that provides us with a benchmark. This can be done systematically. Another way of validating the predictive power of the models is actually quantifying how well they can be actually personalized, because I made statements about personalization and how important it is to have a predictive power for an individual. Well, what if we start exchanging the connectivity that comes from a different patient, and put it from a different subject, and start actually altering this and inserting it into the virtual brain model instead of the subject's own connectivity. So there are approaches we can take systematically in order to quantify the predictive power. Another approach is, and this is something that we are using a lot at the moment, is that we are optimizing a brain model for a particular subject, for a particular condition. Example, epileptic seizures. Yeah, we build a virtual brain model for an epileptic patient, optimize it, and then we take this model and use it in a different context, stimulation, for instance. Yeah? Can we trigger seizures by stimulating in different brain areas? What do the brain propagation pattern look like? Then which means it's a completely different condition. Yeah, so it's across conditions. Yeah? This can be tested in the patient's own brain, in the patient's real brain, and actually validate the type of consequences for the different brain regions. So it's not just to validate the brain model, but to actually provide confidence in the predictive value in clinically relevant conditions, because stimulation is one of the systematic interventions that we do when we try to probe a patient's brain. So this is at the moment one of the most exciting areas, in fact, that we are validating the predictive power of the model across conditions. This gives us a handle on we spoke about causality today during the day. Yeah? So about the underlying mechanisms, have we actually captured something that is mechanistically meaningful in the virtual brain and individualizable?
All right, very cool. Another really exciting thing about the virtual brain is this sort of global network of users that you have, and you know, you mentioned to me that there's about 45,000 users who have downloaded software. How is this network of users contributing to knowledge generation and model refinement?
40,000, a little more than 40,000. I looked it up a couple of days ago. This is measured in terms of number of downloads, in fact. So there is a large community behind that. The virtual brain itself is an open source platform. Everyone has access to the code. And there is a large ecosystem that we have built around the virtual brain. And it's open science. The community can contribute to the virtual brain platform. And it happens, actually. You can discuss. So there is a discussion forum in which guidance is provided to the users, but the users are also making proposals, contributions, and also contributing codes that then is being verified, tested, and sometimes then integrated into the source code. We have a very beautiful example for this, the stereotactic EEG, the intracranial forward solution, so the link between sources and where the electrodes are, has been a contribution by an outside user that has then later on done his PhD actually on this topic. So there are some careers developing around that. The big advantage is that when you have such a large community around that, the community starts testing, complaining, debugging, aiding to debug the code. The virtual brain was released in 2012. So there is now more than 10 years of debugging that has happened. This provides us with a certain confidence that there are no errors in there, which is a very important element that aids to contributes to reproducibility of science. And this is another one of the big challenges, not just in experimental neuroscience, but also in digital neurosciences. So these are the ways of contributing to this. And there are other, the virtual brain is also part of the European infrastructure, EBRAINS, for instance. Yeah, there it's integrated in a large ecosystem of the different softwares. And there it is rendered interoperable with other workflows around data, tools, methods. So this is another, and this is also an open structure. Yeah? So there are other contributions from other laboratories are aiding and guiding the virtual brain through this aspect of interoperability. You always need to adjust, yeah? Which means you can develop, you can evolve, you can improve. It's a community project.
Yeah, yeah, that's very exciting. If we have more time, I'm going to come back to another question related to the data sharing, but I wanted to ask, like, this seems like a very powerful tool for researchers, clinicians, that there may be some commercial interest, of course, in it. But I'm wondering, is what you've developed a one-of-a-kind sort of tool? Are there competing software packages out there that provide similar capabilities to the virtual brain? Or is it something that maybe has been developed for a completely different sort of purpose and like integrate? But are there competitors out there for you?
Software packages that are comparable with similar functionalities? No. That's a short answer. The wider answer is there are software packages that capture parts of what the virtual brain is accomplishing. Example, links between sources and EEG, MEG. There are fantastic packages that are, yeah. But that's just one part. The virtual brain is characterized by its capacity to integrate data, heterogeneous data, structural functional data, perform the simulations, map it to the sources. So this you will not find anywhere else. There are other simulators. The core of the virtual brain, of course, is a network simulator. But there are other simulators, but on a different level of circuitry. Neuron is a very famous and old, actually, very well established neuron and circuit simulator, or NEST, or Arbor. So there are other packages. None of them has such a large community. These are wonderful packages. The large community around the virtual brain is explained by the provision of the larger workflows from the data all the way to validation and inference. Yeah, so personalization, and then inferring new knowledge by operating.
Right. Well, you know, you've mentioned that a core aspect of the virtual brain is that the input is data from dynamic neuroimaging, and you know, you've talked about MRI or fMRI, EEG, MEG, among other modalities. I'm wondering what you see down the road, and what is sort of the holy grail for you in terms of new neuroimaging modalities that would help in refining your model and in taking it to the next level. What's the most exciting and potentially useful new modalities that are on the horizon?
It's actually a good question, actually. It's not particularly new modalities, but it's a combination of modalities. Because one aspect that we are suffering from is the informative power and the aspect of identifiable information that we have in the brain imaging data. We want to extract the information that is and make sure that it is informative. But each imaging modality captures only one aspect of the magnetic field that is being generated on a particular set of sources, etc. The combination of modalities provides us with much better coverage. Simultaneous recording of multiple modalities is extremely difficult. It's possible, but it's in development. What I like to add to this, and this is emergent at the moment, it's stimulation, because you can also now introduce novel stimulation technologies that are being combined with the imaging technology. For instance, you can stimulate non-invasively in the brain in an MRI scanner. This is amazing. Yeah? So it's not just peripheral stimulation, but you can actually target individual areas non-invasively. So it's like pinging a guitar string, and you can start addressing very specifically individual questions. And so this is in development. It's called temporal interference technology, and these things will open up a completely new domain, yeah? Combined with cognitive paradigms, resting state, perturbation paradigms, with multimodal epilepsy. Ask me about the holy grail. Yeah? In my opinion, this will become the most informative approach from which we can benefit. Yeah?
All right. So I have one more question, and then maybe we'll open it up to the audience. And you know, we talked a little bit about this over lunch, but I want to ask you: is there a philosophical aspect to your research? And part of that is, you know, motivated by we seeing that your training started with a Bachelor of Science in particle physics. then you pursued master's studies in philosophy, then you returned to theoretical physics for your PhD. So I'm wondering how that mix of training influences your approach. I could ask you, how does physics influence, your approach to science? But maybe that's a little more obvious. What about philosophy? Is there a certain philosophy to your approach?
I studied particle physics in England, Manchester. Exciting laboratory. I wonder what I want to do, what I'm really interested in, and what I want to do as an academic. And apparently I went back to Germany to study philosophy because the answer was linked to cognition, consciousness. How does the mind emerge from a collection of neurons and networks? So emergence was the key word. Now, how does that translate? So cognition, consciousness emerging from matter. How does that translate into the approach that I have taken? Oh, I went back to Stuttgart in Germany, and I sought out the leading mathematician working on the field of self-organization theories, Hermann Haken, synergetics, self-organization theories. And I was trying to learn the tools and the knowledge that is available in that field. And that is, today we talk about emergence or autopoiesis. Yeah? So since these are the underlying processes, again, in the context of cognition, I acquired this knowledge and then I carried it into neuroscience. And this has accompanied me until today also. The aspects that we describe. How does behavior emerge from this connected network? There are so many limitations. Yeah? Behavior is not just a movement time or reaction time. Or behavior is very complex. And the last 2 days, we had actually quite some in-depth discussions on this. This emergent aspect, yeah, is one of the driving forces. That's the reason why the theory of self-organization, the initial motivation coming from philosophy, has never left me. It's still here. It's determined my path.
Fantastic. Maybe I'll just squeeze in before we open it up that in addition to Hermann Haken, you had the opportunity to work with Scott Kelso, another sort of giant in the field of motor control. What did you learn? What's maybe one thing that stands out that you learned from working with Scott Kelso?
Scott Kelso is a wonderful scientist asking questions about behavior. When he asks questions about the brain, it's always behaviorally driven. He wants to understand behavior. The brain is just an organ in between that helps us to behave. And this is fascinating. And behavior for him is always been the interaction with the environment. His work was inspired by Bernstein and, again, self-organization. That's the reason why I went to Florida to work with Scott. So behavior has to be understood as a dynamic process, and Scott always looked at coordination. Yeah? Coordination between limbs. This is dynamic. Coordination with the environment. What he did, he developed paradigms, often periodic, but then try to extract what the essence is, information. We spoke about this also over lunch today with the other colleagues from the conference. Informationally relevant variables, order parameters, which are the collective variables. So it's informationally guided, not necessarily a physiological measurement. Yeah? So there is a level of abstraction that is linked to dynamics, that is informative and information driven, but highly dynamic. Get rid of the baggage of static descriptions and focus on the dynamics. This has become a drive in my research. And when you look through my papers, it's emergence on the one hand side, but then it's dynamic descriptions. And this is one of the reasons why many of the paradigms that we look at I mean, we look at resting state dynamics. What I'm really interested is complicated, not complicated coordination, but coordination, yeah, in a dynamic sense, because this is how we behave. Yeah? It's not a transition from one state to the other and another state. It's a dynamic process. Scott has always, sorry, this is a little lengthy, but he deserves that. Scott has always emphasized this dynamic aspect of movement. This is what movement is about.
All right, great. Well, let's open it up to questions from the audience. And
Oh, sorry.
We should also mention for those of you who are on the Zoom call, if you want to just raise your hand so that we can see and all of you. We'll flag up for that. Sure.
Thank you. One of the themes of the last 2 days was limitations, going from task paradigms, kind of traditional task paradigms, into real world, actually looking at what the brain does out there. So do you see TBB as a way of kind of reconciling these differences until we get to the point where we can actually image real world? And if so, can you speculate wildly as to what that would look like in the platform?
TBB is extremely sad in regards to real world embedding in
Sadness.
however, yeah, TBB is sad. I really say this out. No, what we are doing with the virtual brain is so far we have very successfully constrained brain activity by individual structural constraints, and then from simulations and mimicked brain activity as we measure it in sensors. It's fantastic brain activity. TBB, we have done a lot on brain activity, whether it's physiological or logical. But we have TBB does not think. The virtual brain does not do anything meaningful. Again, in our hands, this is something that we miss. It's a big shortcoming yet. What are these? We spoke about cognition emerges. This is function. How do we get function in TBB? There, this is a challenge, and I'm discussing this with colleagues in the Human Brain Project. Because when you look at all the applied domain robotics, where algorithmically they're extremely powerful, biologically inspired algorithms, then you have robots, performing spatial navigation, using learning paradigms. Wonderful. It's all biologically inspired. It's extremely far from the brain, in the sense that individual personalized brains, this language, this cannot even be used. So there is a gap, yeah, that needs to be bridged. And we have started trying to get these aspects together. What's in these algorithms that make one of these acting robots useful that we do not have in TBB? How can we get these concepts together? This is an aspect that is missing. And then the embedding in an ecosystem, so embodiment is wrong. To ask me if I can speculate where it should go. In the future, we have to embody the virtual brain, external world, in order to be able to interact. Sometimes it's referred to as digital twin technology. And these aspects can be driven further in order to make it ecologically meaningful, and then even be able to phrase this sort of questions. Because at the moment, all we can do is stimulate. The outputs are extremely primitive. But we have a way forward. There is the technology in place. We can go in these directions. We start handling individuality, that we can individualize these brain patterns, but in terms of activity. So there is a lot of elements that are missing, but there is a way forward. And this is the digital twin technology. So I'm emphasizing the technology. It's very promising.
So it's fascinating, and I'm really not stuck is the wrong word, but just thinking about all the data and programming, and so I have my first question. 40,000 people downloaded it. They're obviously running simulations. Do you provide like a toolkit to help them code the simulation, or is that or what's the next step to make this sort of a ubiquitous tool that people run simulations on?
Okay, I'm not entirely sure if I clear about your question. How can we help the people to simulate better? Is that the direction your question?
How hard is it to write a simulation?
We are not with a TVB, with a virtual brain. It's not a writing tool. It's not a script. It's a simulation platform with associated services. So you don't have to write a script. You can use a platform, but then you can chain it up with other service softwares in order to help you to work better. This chaining up is very important, actually. It's this interoperability. We are integrating knowledge from different domains, and there often own writing is necessary, but it's the interfaces between the individual softwares that you want to connect. Is it hard? You have to have certain skills, but it's not that hard. There are use cases that you can follow. We had just Fidelis gone, a psychiatrist who actually went through all the use cases and who successfully reproduced all these aspects. But the part that is hard is actually the part that is linked to the science. The use of the virtual brain is actually not hard. It's a part that we cannot do for you. It's a part that the virtual brain cannot do for you. Namely, asking the right question and then represent it correctly as correct parameterization in the simulation platform. What is the right question for the scientific question, for the scientific problem that you want to solve? So you have to think of a paradigm. You have to think of a certain protocols. You can mimic something that you see in the real world, but does that actually answer the question? This is a little abstract. We see this over and over again. You have to parameterize the virtual brain, which means this, by the way, another virtual problem of the virtual brain. You cannot just ignore certain aspects and leave parameters open. You have to make commitments, yeah, to degrees of excitation and inhibition, yeah, or just you cannot discuss anything away. Yeah, you have to make a commitment to a particular realization, and this realization provides you with a particular answer. Yeah, and this answer, given all the mechanistic implementations that you have, is the real world answer to everything that you put in there. This is a part mastering. This is a part that is difficult. Mastering the complexity, the understanding of what you're doing, how to operate this. The simulation process itself is not difficult. It's actually the neuroscience aspect that makes it difficult. It's not a no-brainer workflow, but that is great science. Did I answer your question?
Well, just I'm thinking about scaling, and the limiting factor sounds like a consulting practice that helps different organizations understand how to use it, but also how to interpret results from it. That's the other, I guess, bottleneck. Is like, well, I got these results, and what do they mean? How do I use them?
This interpretation of the results is actually, this problem is solved because the virtual brain, you generate the same type of signals that you measure the individual. So what it means, these are the sensor signals of the same nature that you measure in the individual. The question is more, okay, so what do the brain signals mean? Okay? So it's not the output of the virtual brain that is questionable, but it is when you measure an EEG of a subject in a particular paradigm, all these wiggly lines, what does that mean actually? Yeah. This is the challenge. When I responded earlier to your question, and said the challenge is actually on the neuroscience side and not on the operation side of the virtual brain. This is, the virtual brain is a tool. The challenge is on the scientific side. How to scale it up to many other applications? You have to build good workflows in order to solve problems and demonstrate good use cases that successfully know how to solve a neuroscientific problem. That's what we are doing in epilepsy. Find use cases and demonstrate how solutions can be generated. Clinically relevant problems, then you need to adapt it into your own.
I was wondering if you could provide an example of one of those uses for epilepsy. Exactly what was the input, what was the output, and how was it used? Because I'm not really clear on practically what the whole process involves.
Yeah. I can step you very briefly through the process. Yeah? You take a patient, you image the patient, you need structural data, typically MRI, typically of two forms, anatomical MRI and connectivity information, so diffusion MRI.
So you have them do a resting state fMRI?
No, I did not say anything about functional data. Okay? We're talking structural data only. Yeah? And this is actually very important. Yeah, please, for all of you. Yeah? If the virtual brain were rooted in or were relying only on functional data, then we would have information only there where the functional data were measured. Yeah? It's not the case. You know, introducing structural data, this allows us to build an avatar, if you want. An avatar is a non-functional geometric form. You need to equip this avatar with something that is being able to build, put in function. How do you do this? Dynamic systems. So you equip the brain regions with all our neuroscience knowledge. You build from the dynamic systems, neural population models, differential equations, so dynamic systems. You build it into the virtual brain. Now you have made this avatar functional. So it is a virtual brain. It's already a little personalized because you put in personalized data. Is that sufficient? Generally not. Generally not. There are still open parameters that need to be specified. Now functional data are coming in. And you ask about epilepsy. In epilepsy, we provide seizure data. Yeah. And seizure data, there we take the model, the seizure data, and put it through workflows, in our case, inference, Bayesian inference workflows that estimate the parameters in the virtual brain for this particular seizure type. The parameters are typically epileptogenicity. So this is the epileptogenic zone in certain areas where the epileptogenic zone is low, epileptogenicity is low in some areas and high in others. This is the information we get out of this, and we give this to the clinician. Epileptogenic zone is what the clinicians are interested in for this individual subject, because that is a target for surgery.
EEG that you put in?
That's EEG. EEG, you can also, now we're talking non-invasive.
For the example, what was the information that you put in? Is that you said it was
SEG seizure data. When you take EEG, you're non-invasive, and there you run into the issue that the information you get from EEG resting state is not informative about what you want to have, namely the epileptogenic zone. So you need seizures. Very often, generally, you do not measure ictal activity when you have EEG. Maybe some ictal spikes, interictal spikes. So you need to find ways of actually being able to measure non-invasively seizure activity or some other form of activity that is sufficiently informative in order to find the epileptogenic zone. This is one of the hot topics. We spoke about this earlier, yeah? And it is possible with these non-invasive techniques, you can actually trigger seizures, yeah, with the EEG cap on. And then you have propagation of seizure activity through the brain. This is part of the clinical routine. And this turns out to be informative for non-invasively, informative for the virtual brain algorithm to estimate the epileptogenic zone. So, but this is future. Yeah, this is ongoing research with projection over the next 10 years. But it's possible.
But now isn't the output that you can say where this seizure originates now? Isn't that something?
Is then the output. You asked me about input and output, right?
So I just,
Output is where is the epileptogenic zone, how it's organized. This is the output. We can get this out of this process.
did you say that they can induce a seizure?
Yes.
And how is that done with electricity into electrodes?
There are multiple usually in clinical routine today, it's done with intracranial electrodes. This is part of clinical routine. When you don't have any seizures, you stimulate the different electrodes in order to trigger a seizure, to sample the degree of epileptogenicity. What is not being done at the moment in clinical routine is to do this non-invasively, because the existing stimulation techniques are not good enough, they're not focal enough, they're not deep enough. All this is changing with evolving neurotechnology. Today, in particular in the domain of temporal interference, multimodal temporal interference, technologies that have been developed for the last 2-3 years, you can become as focal as in deep brain stimulation, non-invasively. And this, like you ask questions about scaling up, suddenly it opens the door to Parkinson, epilepsy, drug-resistant depression, Alzheimer's disease, and all non-invasively through stimulation techniques. So this will be a huge opportunity. Eddie.
Yeah, I want to just scale up a bit more from that. Yeah. And this actually comes from the fact that we've been spending the last 2 days talking about dynamic neuroscience. And certainly, we've seen this thing, phrase where epilepsy is considered a dynamic disease or a network disease. And certainly, I think in terms of success in translating dynamics to a model, and then from a model to an application now is actually at the heart of the clinical trial, which you've been mentioning in France. Are there lessons from that journey that you think can translate in terms of a dynamic approach for other clinical applications?
Yes.
Okay. We're done. Let's go to here.
Did you have a question?
Shall I elaborate? Go ahead and finish.
Shouldn't be so rude.
Let's number one. Let's number one. It's different. In particular, there are multiple things that get do better. Do not be naive about your metric. Why is epilepsy? No, epilepsy is difficult, but in terms of feature that you're looking at, that you extract from the data, in epilepsy, you can see it with the naked eye. Try to do the same thing in resting state for Alzheimer's disease patient. It's impossible. You see nothing, or even for a healthy patient, subject, absolutely nothing. So you need good data features that are sufficiently robust, that can be that are informative for the again scientific question. In multiple sclerosis, where are the lesions? How do they affect the reorganization, the pathological reorganization of the activity? Things like this. So the data feature must be informative. Resting state is not informative. And we find this even in simulations from the virtual brain. Quite a large number of pathologies, it's not informative. Now I'm getting back to the stimulation. You can actually stimulate the brain and render it informative. So it's a metric. This is what we learn. You have to have a good metric that captures the meaningful information that is in the data. This will vary from one disease to another one, and it will vary also in terms of the brain imaging technique. This is number one, what I wanted to emphasize. Number two, give up optimization approaches. No, that's maybe too hard. accept the fact that there may be multiple solutions to your question for this particular patient, and not an optimal solution. Because given the information we have, all the knowledge we have, all the data, we put this together in our inference framework and try to infer what is a parameter distribution, how is the epileptogenic zone organized. It is not an exception, but the rule that we have equally good solutions for this particular patient. That's not very satisfying, because you either operate or you do not. Yeah, you have to make a choice. But this is something that we need to accept. We provide this information to the clinician, and then it's the treating clinician that has to move forward from this. But this is something that we, in a culture of where we want to optimize and provide a singular solution, this needs to be accepted. And once again, this is not the exception. In fact, this is actually the rule. And even in such a dynamic disease as in epilepsy, I suspect that in other pathologies, it will be more difficult.
I had a question and a little bit of comment. When I was doing my doctoral work, I worked with a neurolinguist and was looking at narrative embodiment of experience in its relationship to brain. And you mentioned that embodiment was something that you foresee the virtual brain working towards. I just want you to speculate on how far from now do you really think we are?
The statement of embodiment was triggered by Sarah's question about the more realistic scenarios. How far are we from this today? The current state of the art is that there are individual different software modules that can represent the outside world. For instance, in the context of stimulation, you can have one software that is able to locate the stimulators outside in the world. Then you need a physics simulator that actually is simulating the physics of the electric field going from the stimulator to the neural tissue that comes from the virtual brain. So this is another simulator that you need to run in addition to the virtual brain. Talking about this electric field and tissue interaction, I'm not even addressing it. Having said this, this is just an example for in a very simplistic situation, you already need to link up and cooperate multiple different simulators, unless you write everything from scratch. Yeah, but this is not the approach. I'm involved in EBRAINS, the digital neuroscience infrastructure that I mentioned earlier. And in there, this is one aspect that I'm insisting on to develop a platform that allows us to cooperate different softwares, because there are wonderful world simulation softwares. And video games is being used the whole time, and representation of the external world. And there are already some use cases where colleagues of mine at the University of Munich around Alois Knoll, they have a skeleton representation of a mouse. And they put in a brain network that is actually controlling the muscles, allowing to mimic laboratory experiments such as whisker movements or the movement of a paw. Yeah? Or another colleague of mine is taking this type of mouse in a more simplistic fashion, have it navigate in a virtual gaming environment where the virtual rodent is looking for objects. So in very simplistic environments, in that case, the latter case, it was 100 neurons. Yeah. So very simplistic environments, it already exists, but it is proof of concept that it can be scaled up technically. And this is exciting. You asked me to speculate. With the current development that we have, in particular in terms of software, particularly with gaming software, world representations, and what is happening at the moment with the virtual brain, around the virtual brain as cooperating the different softwares. I could imagine in 10 to 20 years, we have very realistic looking like environments where very highly realistic input-output relationships between the virtual brain as embodied in a complex world can be studied. But there are technical challenges. It's not 10 to 20 years. So the first proof of concept studies already exist. Simplest.
Fascinating.
We'll just give an opportunity for people who are on Zoom. There are some questions in the chat.
So we have two questions from Zoom. First from Yukino Mori. Yukino is wondering if, Victor, if you see potential for the virtual brain expanding wider globally, so outside North America and Europe. And if so, what are the potential challenges of that?
Outside of what? Outside
North America and
North America
And Europe.
in Europe. Yes, we are interacting. So that's a geographic question. Yeah. Okay. We have collaborators in Australia. In Japan, we have interaction with our Japanese colleagues that would like to build a marmoset virtual brain. Yeah. So there is activity in this domain. The China Brain Project has contacted us, has approached us a few weeks, maybe 2-3 months ago, and said, can we meet? Can we have a one-day workshop? And interact and present our approaches and see if there are possible synergies of collaboration. The approaches are different. American Brain Initiative is focusing a lot on different neurotechnologies. In China, there is a large investment in computing power, but also in data collection, in-depth data collection. So that was very impressive what I have seen. There are aspects where we can benefit from this type of collaborations. So there is no coordinated action worldwide, but interaction, exchanges. It would be a shame if we do not benefit from the international synergies that we have to reinvent the wheel every single time. What I wish to highlight is what we have with EBRAINS in the virtual brain is this aspect of workflows where we're putting all the things together. The other projects I see focus on data, focus on neurotechnology, wonderful elements. It's us that are putting these elements together, hopefully to bigger whole that is being meaningful, is generating other information, new knowledge to accelerate the generation. This is the way how I see it. So there are interactions.
The second question comes from Mina Hill. Mina Hill says, I am trying to find out how consciousness emerged from neurons. Did you analyze physical reactions of neurons as well as chemical ones?
Okay, I'm trying to find this out also. Yeah. Consciousness is a very difficult. And it's an exciting topic. There are multiple ways of approaching. Consciousness can be quantified and characterized in different ways. There are essentially two aspects. One of them is linked to self-awareness. And another aspect is linked to awareness, as in when a clinician asks you, are you conscious? You say, yes. What is your name? My name is Victor. So elements in this. The second aspect is simpler to handle and can be controlled, can be parameterized through anesthesia, for instance. And there large progress has been made, large strides forward that tell us also, that teach us about what type of activity is actually associated with different levels of consciousness. This is typically involving neuroelectric and neurochemical activity. This is absolutely true, because as you go through this parameterization and the individual brain states change, this is like a parameterization in the model. And there, quite some representation and modeling has been done that captures the sequence of the individual brain states. If you go into the domain of self-awareness, more linked to philosophical aspects thereof, existential aspects, this is more complicated, but there are also some activities in place. I'd like to highlight the work of Julian Robinovitch, or in France, Jean-Pierre Jean and Stanislas Dehaene. So these are people that have taken very orthogonal approaches, trying to quantify this. Typically, that goes in terms of metrics, trying to provide a formulation for what consciousness is. My question.
I may ask another, I'm curious about the data, how you get the data for this. I mean, it's obviously data is a big deal, like the better data you have, and growing the data set will make it more accurate. So you have all these people who've downloaded, that doesn't mean they're all providing data for it. So how are you growing the data? And from a data ownership point of view, how does that work? Like, how do you depersonalize it? How do you depersonalize it, but still keep it so that you can choose gender or age or, you know, a modality, whatever it is?
It is a good question. Again, you have the scaling up in mind.
Sorry, I was going to make you work.
This goes way beyond the virtual brain. There, I'd like to answer in the context of eBRAINS, because eBRAINS has been created essentially for this. For those of you who do not know, eBRAINS is a European infrastructure, digital neuroscience infrastructure, that has as a general objective to help the research community to generate new neuroscience knowledge through the integration of digital tools, data, and models, and through, in fact, the integration thereof, so making them interoperable. And it is an output of the Human Brain Project. It was a large project, or is still a large project in Europe, 10 years. It was funded with almost €1 billion. And now this infrastructure is in place. And it is this type of infrastructure that can address these things. You have to have data in there. Then you have to distinguish data and health data. So there are certain rules for security have to apply. This is a huge undertaking, actually, to protect the individual patient data, nevertheless warrant access to people to operate these data. There are multiple solutions to this. Nothing that works perfectly yet. It's an ongoing process. So there are certain firewalls, there are certain conditions you can actually access this type of data. Even more importantly, once these data are in place, so there are large data structures are being built. And there are databases and infrastructures that are responsible for these data that do exist. But what you want to do is you want to get them into eBRAINS and take advantage of the interoperability with all the other tools. And there at the core is actually what is an atlas, because you need to represent these data that come from many different modalities, from many different subjects, but you need a brain reference space in which you represent them. Hippocampus, CA1 region of the hippocampus covering from different labs. You need to get this knowledge and the data in there. I said knowledge, no, the data in there and represent. This is happening, but you want to also put additional knowledge in there. And In this sense, knowledge can be formalized and expressed in a formal, in a symbolic, in a mathematical fashion. Typically, we call this a model. So all the neuroscience knowledge that we have, we express it as a model. This must be also interoperable with this atlas. Represented in this atlas, so the data can inform the model. These are the workflows that can then be used for validation, inference, that you need in this huge infrastructure that has a capacity to integrate this. And then it's scalable. Then you can scale it up. But you cannot do this on a single project level. You really need something like a infrastructure that is supported by a government or by Europe, so by multiple governments, because it's a huge undertaking.
All right, well, this has been a fantastic conversation, and thank you, Victor. Thanks to the members of the audience, both in person and online, for their excellent questions. Thank you,
Thank you, Steve. Thank you, Victor.
Thank you,
Everybody on Zoom.
Thank you.